All right. So we left off looking at caloric values being transferred from food calories to heat calories. So next thing we want to look at is caloric food values. And hopefully we're pretty familiar with this. If you look on the back of a label, on that label for food, it tells you three major areas and then some little details about each of those areas. But like carbohydrates, protein, and of course, fats, right? And then of course, fats will be broken down into saturated, unsaturated. Carbohydrates might be broken down into complex carbs versus non-complex carbs versus sugar, alcohol, and just sugars in general, added sugars and natural sugars. Typically, protein's not broken down by too many things because protein's simply protein, but there is a value that is associated with that for heat. And so for 1 gram of each food type, we get carbohydrates. It looks like my slide has shifted here in this view. It's 4 kcals per 1 gram. So this should be 4 kcals, 4 kilocalories divided by 1 gram. So for every gram of carbohydrate, it will generate 4 kcals of heat. For fats, we see 9 kcals of heat, and for protein, back to 4 kcals. And again, this is another one of those things you're going to want to write down somewhere. Typically, the questions are going to ask you to break a food stuff down and look at what that value is going to be. And so that's exactly what we're going to do. So here are some foods broken down by the type of food and what type of materials in the food, and then approximately how much energy that it's going to give you. So for instance, if we look at the very top one here, it says a banana, 1 medium banana. And then notice the value over here is in parentheses, and that means it's approximate. So we've been talking about significant figures, and ironically in this twist, we don't worry about significant figures here because it starts off right here with banana, 1 medium. So if I had the whole class go over to the Wawa across the street from school and each buy 1 medium banana and bring it over back to the lab, I'm sure that each one of those bananas is going to be slightly different. And so when we take that into account, we end up with an approximate value. But if we look at a banana, we can see that it's got 26 grams of carbohydrate, 0 grams of fat, and 1 gram of protein. So if we want to figure out what the caloric value for that banana is, then what we would do is use those numbers we just had, the 4 kcals per gram, 9 kcals for the fat, and 4 kcals per gram for protein, and we'd simply apply it. So 26 times 4, right? That would be 104, 0 fat, and then 4 for protein. So 104 plus 4 gives us 108, which is approximately 110. So that's exactly how that would work. You're just going to multiply carbohydrates by 4 kcals per gram, the fat by 9 kcals per gram, and then the protein by 4 kcals per gram. A typical question might look something like this. How many kilocalories are in a piece of cake that contains 25 grams of carbs, 5 grams of fat, and 5 grams of protein? And so what you would do is you would take 25 grams of carbs multiplied by that 4 kcal per gram. Here we'd see the grams would cancel out. We'll then add to that the 5 grams of fat at 9 kcals per gram. Again, grams would cancel out. And then finally, we would add the 5 grams of protein to that at 4 kcals per gram. When we sum that out, we get 165 kcals. Now, on these questions, again, sig figs aren't really going to come into play here. Again, it's simply because they're going to be approximates, right? So this is an approximation for this piece of cake. Now, before we go any further, remember we want to take that heat and say, well, we can only measure it by a heat change or a temperature change. So I want to make sure we spend a little time about temperature here. And what we're used to and what we're going to be using are usually two different things. So the metric unit for temperature is going to be what? Anybody know? That's right, Celsius, right? That's going to be the metric unit that we use. Remember, if you go back into chunk, I think it was 3 or 2 or something like that of the last chapter, we saw that it was Kelvin or Celsius were going to be metric temperatures. And here in the United States, we don't use that, do we? What do we use? Right, we use Fahrenheit. Now the two are related, so we can convert between the two. And so again, typically I tell students, if your calculators can sometimes do this on its own, and if you need help with that, just ask. But typically you can find it in the directions. There's a couple different key switches you can hit, and boom, you have the temperature conversion between the two temps. If you don't have that key, then here are the two conversions you can use. So if I want to know the Fahrenheit temperature, I simply take the Celsius temperature, multiply it by 1.8, and add 32 degrees to that. If I want to know the Celsius temperature and I have the Fahrenheit temperature, then I'll subtract 32 from the Fahrenheit temperature, then divide by 1.8. And for this one, we actually want to make sure that we're following our points here of math. This should be in parentheses. That way you're doing the subtraction first and then dividing by 1.8. All right. So let's do some conversions together then. I want to convert 42.5 degrees Celsius to Fahrenheit. So I'm going to go back to the previous slide. I'm going to grab that formula there and simply plug and chug into that formula. So I'm going to take 1.8 times 42.5, and then I'm going to add 32 degrees to it. So I'm get 76.5 plus the 32 gives me 108.5. Now at this point, again, I do want to worry about sig figs, but we're going to follow a very simple rule for sig figs. And that is whatever place the temperature was in before I made the conversion, that's the place I'm going to keep when I'm done. So here we went to the 10th of a degree for Celsius, then our answer is going to go to the 10th of the degree for Fahrenheit. So the rule's a little different for temperature. Again, I don't want to be too concerned about that right now, but you do want to practice your sig figs, and it will be important for most other measurements. Now, when we convert from Fahrenheit to Celsius, we're just going to use the other formula now. So now we're going to take that 78.5, and remember, I want to do that division first. So here you can see, I'm sorry, the subtraction first. So here you can see we're going to do subtraction first. So we're going to take 78.5 minus the 32. We'll do that initially, and then we'll divide. And that gives us 46.5, and then we'll divide that by the 1.8, and that gives us 25.8 degrees Celsius. And again, we're running that the same way, where we're going to have the 10th of a degree in Fahrenheit, so we're going to have the 10th of the degree in Celsius. All right. Now remember, the reason why we're going to be doing these things is we want to be able to calculate the heat from an object. So we're going to raise the temperature up and we're going to see what that heat is going to be. Now, specific heat is another thing that's going to come into play. So specific heat is going to be material specific. So the amount of heat needed to raise the temperature of exactly 1 gram of a substance by exactly 1 degree C. And we abbreviate that as SH. Now I know that seems kind of complex, that's a lot to digest mentally, but realistically you understand this. So if you go to the the drive-through to get a lunch or a dinner or something along those lines, and we order a meal, typically we're going to get a value meal. So if you head to a Chick-fil-A, let's say, you end up with a chicken sandwich, some fries, and a Coke. What is it that you want to eat first typically? And most of us would say the French fry, right? Especially if you're at like McDonald's where the fries are really, really thin, because the material doesn't hold heat as well as, say, the sandwich or the nuggets. And so you want to eat the fries while they're hot, and so you eat those first because they cool down the quickest. That is a function of specific heat. Okay. If you've ever done insulation for a home, then you're looking at R factors. Those R factors are based on the insulation value, or how easily or how hard it is to change the temperature of the material. So water is an excellent insulator, right? We can heat water up and water will hold the heat for a while. Okay. That's because of the specific heat of water itself. So every material has a specific heat. Now, when we go to use specific heat, what we're going to do is we want to calculate the amount of heat that's going to be equal to the specific heat, which is coming from that material, times the amount of material. Now remember, we've said this before, it's easier to heat up a quart of water than it is a gallon of water. So the more water I have, the harder it's going to be to change the temperature, the longer it's going to take, right? So water has a very specific heat. Then how much water do I have? And then we're going to look at delta T. Delta is simply the change. So we can have delta for anything, the change in temperature, the change in time, the change in mass, the change in speed. We can have change whatever we want. So delta is simply final minus initial, right? So we would write that out as temperature final minus temperature initial. And that's what would be equal to delta T. And delta is simply a little triangle. And it's the Greek letter delta is where that's coming from. All right. Now, calculating specific heat. How many kilocalories of heat are absorbed when 85 grams of water is heated from 45 degrees C to 61 degrees C? So remember, you'll have that formula at your disposal. We know that heat is equal to specific heat times mass times delta T. And they're asking us for heat because they're asking us for kilocalories. So we know that kilocalories is a unit for heat, which means we're going to be solving this directly. So we're going to be plugging and chugging these other numbers in. So the first thing I'm going to do then is, what is the material? Well, here we're told it's of water. So we know we're looking for the specific heat of water. Well, water has a specific heat, and it's going to be 1 calorie per gram degree C. That's a huge unit. Sometimes can confuse students, but water then, or specific heat, is going to have 1 calorie per gram degree C. Okay, so it's heat, mass, and temperature. Right? And of course, we need all these units to work out. And so that's why specific heat then has to have this weird unit. If we want to end up with heat, that'd be calories. We need to get rid of mass, which is grams. And then of course, degrees C, which is temperature. So all the units have to work out. Well, that's going to be our specific heat. And again, that's specific to water. So if I was using a different material, I'd have to have a different value. And either I'll provide that value in the question, or you can look that value up, or sometimes I'm asking you to calculate specific heat, and we'll see a practice problem with that as well. All right, so we know that specific heat then is 1 calorie per gram degree C. And then we're told mass. We need the mass of the water, so we go back into the question. Heat are absorbed when 85 grams of water. So we know it's 85 grams. That's going to be our mass. And then delta T. Now, delta T is not either one of these temperatures. Remember, it's the difference between the two. We want to take the final, the 61, minus the initial, 45. The difference between those two will be 16 degrees. Now, what's really going to be different is if this was switched. So if I heated the water up, right, then it would be, or if I cooled the water down, it'd be 61 to 45. Instead of heating it up, I'm going to cool it down. So now I'm going to get a 16-degree difference, but it's going to be a negative sign. Now for our courses in the basic chem and the general chem, we don't worry about that, but that's going to produce a negative heat. That negative is simply telling us whether the heat is going into the system or out of the system. That's a little bit of a complex concept there. We reserve that for our 150 classes and above, but so you don't have to worry about that. When I ask questions, typically of these, I'm going to be asking for an absolute value. Notice up here I said how many kilocalories of heat are absorbed, right? So you can give a positive number because it's an absolute value. I could have said how many kilocalories of heat are lost, right? Or yeah, lost would probably be the best way to put that statement. So are lost when 85 grams, and then I would say cooled rather than heat. So again, don't worry so much about signs down here, but that is what's going to happen. So you can always take the big number minus the little number. That's going to give you your heat change, your temperature change, and you can use that to calculate your heat. Once you get to this point, it's using the calculator, right? We'll let it do the heavy lifting. We'll take 1 times 85 times 16. That gives us 1,360, but let's keep track of units here. It's calories per gram, grams canceled out, degree C canceled out, so we're left with calories. Now remember, what did the question ask us for? How many kilocalories of heat? So we're gonna have to make a conversion there. So heat then would be equal to 1.36 kcals. Now here I cut that 0 off. Now was I actually allowed? Well, that's cleaning up the problem, so let's figure that out. Let's see, here we have one significant figure, but actually this is an absolute value for water. It's exact. All of our specific heats are based on water, and we assume that water is 1. So we set the scale by water. So we have as many sig figs as we need for that. 85 grams, there's 2 sig figs. 16.0 degrees C, that's 3 sig figs. So how many sig figs are in my answer then? We have unlimited, 2, and 3. Then we're going to apply 2 to this answer. So that means our final answer then will be 1.4 kcals. All right, now I know it's always going to look easy when I do it, and I'm doing it on this screen-o-matic here, so you're easily able to follow along, and it all makes perfect sense. So now it's time to see, did it actually make sense? So here are a few problems, a few more practice problems. Whoops, sorry, I did another one in joules for you here. And then I've got three, it looks like. So three problems that came off of old exams. So make sure you look over those. I'll put those in a separate chunk. So if you want to go back and look at those and get the answers for those, and see how you did, you can stop it. I'll slow it down. I'll do each one on a slide, and that way you can see how I worked out the problem and then compare it to what you did. All right. So if you have questions about that, make sure you get a hold of me. If you want more practice problems on specific heat, let me know that as well. I'm sure there'll be some more practice problems in there, but if you do exhaust that list, feel free to try your chapters. At the end of the chapter, your textbook. And again, if you contact me, I'm sure I can give you more practice problems or sit with you and make sure you're doing things in the right manner. All right. So we'll stop here. Next would be matter. So we'll change gears and we'll finish out this chapter with that next chunk. All right. Talk to you soon.